Terrific. We're going to do a quick recap about our notes from chapter 12 around sound, and we'll take a look at the things that we started last time. There we go. Sorry, excuse me. We started off by taking a look at the speed of sound and talked about the fact that it's a constant velocity, but it does depend on the material. And then we also took a look at some common vocabulary terms. Then this was a place where we spent a little bit more time, where we talked about the two different kinds of weight measuring how loud something is. And sound level, and this is important, I'm going to underline this, sound level is also referred to as relative intensity, whereas intensity in watts per meter squared is simply the SI measurement for intensity. So intensity is a combination of how much power there is and how spread out that power is. But sound level, or again called relative intensity, means relative to the threshold of hearing. So that's why the term relative intensity is used. A little bit of math. You probably took a little bit of hunting to find out where the log button on your calculator was. But on the quiz, you ought to be able to go back and forth between relative intensity and intensity. And I did a couple of examples last time. We also talked about key parts of the ear and hearing. We also talked about the reason why your ear can hear very faint objects, but also hear really, really loud objects without breaking, is because of muscles that surround this cartilage, this sort of mechanical amplification that happens. And when loudness increases and gets to dangerous levels, because remember, if something's loud, the eardrum is shaking back and forth. These pieces of cartilage are rattling, vibrating really quickly. And worse, they're vibrating with a large amplitude. So what happens is that your ear, when it senses this, will clamp down on muscles around these cartilage pieces and help suppress the vibration. Excuse me, I was losing my voice there. Okay. We talked about the quality of sound, and musical instruments essentially create vibrations, and then the instrument itself will enhance some of those vibrations. We looked at the harmonics of a string fixed on both ends in chapter 11 and noted that those harmonic frequencies are actually always present. They're just not as loud as the fundamental. And different instruments will amplify them to different extents. I uploaded a link to a video which was very informative about the difference between these instruments that act like closed pipe resonators and open pipe resonators. And I found that to be very interesting. So open pipe resonators have harmonics that are very similar to a string that's tied on both ends. But a closed pipe resonator has harmonics that go as odd multiples. And that's because in order to get resonance, you add an extra node. But in this situation, the fundamental frequency is a quarter of a wavelength. The next harmonic that experiences resonance will have 3/4 of a wavelength and 5/4 and so on. So that's how come different instruments have a different characteristic pattern of frequencies. And the same thing could be true with voice. So I spent a little bit of time talking about how voice recognition works, how high frequencies show up more with hard sounds and low frequencies show up with soft sounds, even though you're saying it with the same pitch. Now, tonight, the new piece is about the Doppler effect. The Doppler effect applies to moving sound. And of course, motion is relative. So it doesn't really matter if it's the source moving or if it's the observers moving. And essentially, the idea is that if the source is moving and it's creating these oscillations, the next time the next oscillation gets made, it's sort of chasing the sound waves it's producing. And that means that the observer is going to hear the waves closer together, which is going to correspond to a higher pitch, and vice versa. Observers who are on the back end of this will hear a lower frequency. So there's a nice little simulation you can feel free to paste in. But I find the Doppler effect conceptually is pretty easy to understand. Mathematically, though, there's a little bit of challenge. So in this case, we have our source that's moving. It produces a sound wave that travels this far from when it was produced. And then at point number 2, the next wavefront is produced, but our source has been moving. So the perceived wavelength is actually shorter than if the source wasn't moving. So we can see that the wavelength is going to get shifted, but when we hear sound waves, we don't really perceive the wavelength very much. We perceive the frequency or the pitch. So it would be worthwhile to have a Doppler effect equation that is based on frequency. So if our observer is moving, it's the same idea. Our observer is going to encounter the wavefronts more often and hear a higher pitch. And motion is relative too. So if objects are moving away, then they'll also see a frequency shift. Now, this takes our Doppler effect equation and then breaks it down into 4 different scenarios. These 2 are for the case that our observer is moving. These 2 are for the case where our source is moving. If the observer is moving toward, then we're going to get a higher frequency. So VO stands for the velocity of the observer. And you see we have a plus and minus in the numerator and a minus plus in the denominator. That means that you need to make a choice. So if the observer is moving towards the source of sound, then they're going to hear a higher frequency. So we pick the choice that's going to lead to a higher frequency. And since VO for observer is in the numerator, we pick the plus sign. And the inverse argument can be made for moving away. Choose the minus side because that'll make the numerator smaller and we'll have a Doppler shift that's smaller. If the source is moving, same idea, Vs stands for velocity of the source, but in the denominator, if we're going to make a shift to a higher frequency, then we need to make the denominator smaller. That's why the minus sign is chosen. And the inverse argument, again, is for a plus sign if the source is moving away. So let's try an example really quick. I'm going to change my video source to be my document camera. And then stop sharing. Well, that's interesting. So let's try that again. Maybe I have to go through the other camera first. Or maybe I have to share screen. And then stop share.
I think it worked.
I'm
Okay.
seeing the document camera now, and I was before.
Oh, you were? Okay, it was just different on my screen. But that's okay. Thank you. Thanks for helping out, as always.
Might be blurry, though.
All right, let's do the following. I'm just going to start off with our situation first. So we have Let's see. Oh, let's do a bat. I like bats. So I'm going to try and draw a bat. Okay, better?
Yeah.
Okay. Let's see. So we'll put our person over here, a stick figure person. And our bat's flying along, and we'll give the bat a speed. And let's say, well, actually I saw a bat flying around the house last night, which is really great because bats are in big trouble here in Vermont. They're subject to something called white nose syndrome. When they hibernate, especially little brown bats that hibernate in caves, when they um, when they hibernate, this fungus starts to grow on them, and normally they would hibernate all winter long and then come out and be super hungry because they get really fat in the summertime normally. But they wake up because this fungus is growing on them, and they try and groom the fungus off them, and it takes up a lot of energy, and then they're awake in the middle of winter and they go out and look for insects and they can't find any, so it's pretty sad. So anyway, be kind to bats. So let's suppose our bat is emitting a sound frequency, and we'll put it right at the threshold. Usually their frequencies are pretty high, but let's say it's 50 kilohertz. I just wanted to use a bat because my next example is going to use a bat as well. So what would be the shift that this person experiences? So we know we're going to have a shift that's higher. And so our general equation looks like this. Our shifted frequency is going to be equal to v, which is the speed of the wave that we're talking about, plus minus VO over V minus plus VS times whatever the original frequency is. So we need to make some choices. And the choices are going to become, well, the observer is not moving, so VO equals 0. And the speed of sound that we're talking about is the speed of sound in air, so that's 343 meters per second at standard temperature and pressure. And our unshifted frequency is 50 kilohertz. So F prime is equal to 343 divided by 3, our source is moving, that's the bat, 343 minus, we elected the choice of minus because that's going to make the denominator smaller and give us a frequency shift that's up. Right, so it looks just like this. And I can go ahead and just stick with a 50k hertz because that should work out just fine. And 343 minus 15, boom. Then I can go 343 divided by the answer I just got times 50. Because I know the frequency is going to be on the order of kilohertz anyway. Yeah, and so I get 52.3. Okay, looking good? Okay, great. So I'm going to shift boards here. And do a different example. And in this case, we're going to have a bat again, like drawing bats. They're really pretty cute.
Bats are cool.
They're cool. I have a funny story. I'll tell you the funny story while I'm drawing the bats. This bat has ears. And we, at my day job, we won a grant to make what was called a smart bat house. And so we used an Arduino and Raspberry Pi. These are all for really geek people, but we put sensors in the bat house. So we built a nursery bat house, which had 4 layers. And got a bunch of students involved. We're broadcasting the data wirelessly, and we worked with several bat experts. And after we installed the bat house in the perfect place, then the bat expert came out and said, "Oh, you have the perfect location. Everything's awesome. I can't wait to see what kind of data you get." And then he said, "But you know, the bats have to find it first, and there aren't that many of them left. So it might be a few years before you get any bats." Duh! And here we are in year 7, and we still haven't seen any bats yet. So very sad.
Oh,
Oh.
Gotta be patient, I guess.
Yeah. I don't even know if it still works. I have to go out and check it. Anyway, the bat is trying to use sound waves to pick up an obstacle, but counts on the reflection. And bats are so cool that they can actually use the time of flight of the sound waves to measure how far things are away from them. But it's even better than that, because they're so good at listening. They can also determine the speed of their target, their prey. So they can actually, how, like if people playing sports, passing a ball from one person to another, you sort of have to lead them if they're running. And bats actually track their prey like that. They can anticipate which way they're going. Very successful. Now, they're going at 15 meters per second towards this wall. And the reason I did 2 sets of sound waves is because the bat's listening for the echo. But when the sound waves leave the moving bat to hit the wall, they're coming from a moving source. But when the sound waves come back at them, they become a moving observer. So I call this the double Doppler. 2 Doppler shifts. So what's that going to look like? What does the bat hear? So we'll assume that, again, we're talking about 50 kilohertz. And then that way we can compare this answer to the one we get. So the double Doppler is going to look like this. We're going to have 1 Doppler shift. And this is a moving source. So it's going to be a shift that's higher. So this is going to be V over V minus Vs times F. But then we're going to have a second shift, which is going to be applied to this. So the prime indicates the shifted frequency. So it's a double Doppler. I'm going to use F double prime. And now it's a moving observer. So that would be V plus VO over V times F prime. Well, wait a minute. There's got to be an easier way around this. So what if we take this equation and substitute it in for F prime? So that's going to look like this. F double prime is equal to V plus VO over V. And now instead of writing F prime, I'm going to write this formula for F prime. So that's going to be V over V minus Vs times V. And lo and behold, the V's cancel out. So you could actually, in that form of the Doppler equation where you have plus and minus in the numerator and minus plus in the denominator, you can actually do those at the same time. Double prime is going to be equal to V plus VO over V minus Vs, and VO and Vs are the same number, times F. So just one more line. 3, 4, 3 plus 15 over 343 minus 15. And actually, this case of the double Doppler shows up a lot because um, Doppler radar that's used to detect rotating storm systems will uh, do the same thing. If you're driving down the highway and you see officer friendly shooting their radar gun down the highway, they're going to get a double Doppler shift. All right. So it looks pretty good. Let's see what this turns out to be. Hello, calculator. Okay, so I know that 343 minus 15 is 328, and 343 plus 15 is 358. Okay, interesting how that works out, right? So 358 divided by 328 times 50. So 54.6 kilohertz. Okay, great. Give me a shout if you have any questions about where those numbers came from. If you want to take a screenshot, that's probably a good time. Okay, good. All right, give me a thumbs up if you're ready to go on.
Yep.
Cool, thanks. Okay, well, I'm gonna change video source and we'll go back and we'll finish out the notes and see how we do. Thanks, Sid. All right. And share screen. All right, cool. So shock waves, or sometimes called bow waves or sonic boom, happen where our source is traveling faster than the speed of sound. And essentially the idea is that the source overtakes the sound waves that are being produced. So instead of just getting the sound waves more often, we get them all at the same time. And that's why we get a boom out of it. This is very similar to the wake produced by a boat. It's interesting to note, again, properties of waves say that the speed of waves depends on the medium they're traveling through, not what made them. So the speed of the boat might have an impact on how big the wake is, but it doesn't change how fast the wake travels. And with a sonic boom, it's the same idea. And sometimes there are multiple booms just because different parts of the aircraft are displacing air. Sonar is super interesting. That's actually the source of my graduate research was in ultrasound. We came up with a way of measuring the heating associated with ultrasonic applications. At the time, the technology is relatively new. And so if you were trying to determine the gender of a child, for example, then we just turn up the intensity. But our research showed that actually when the sound waves traveled through embryonic fluid and hit a hard surface like a skull, it actually would create heating at that particular point. And by as much as 5 degrees Celsius, which is not great. So these days, ultrasonic machines usually, I'm not sure exactly what the controls look like, but it takes into account the potential heating that's caused by a particular application. But it's still the same thing that the bat did. Pulses go and travel back. And based on the time of flight for the sound waves, you can figure out some interesting stuff. Now, Doppler ultrasound is also very interesting. This is typically used in diagnosing arteries being clogged, because remember from our chapter on fluids, if you close down the aperture, the opening, the cross-sectional area, then that requires the fluid to go faster. So if we can measure the velocity of blood flow, you can tell if someone's experiencing an issue with clogged arteries. Yeah, so that's it. That gets us to the end. And for those of you who joined after I started, a quick reminder, I'm going to need till probably about Sunday to finish grading all the quizzes. And my grades are due on Thursday. So I would encourage you to go back in uh, on, say, Monday and just check. And if there's anything that doesn't show up as graded, then it might be because I left feedback because the answer wasn't 100% right. And then you can go in and fix it. I can't grade them because then, well, I could grade them because I made them all multiple attempts, but then you'd have to upload your stuff again. And I think that's kind of annoying. So anyway, we're figuring this out as we go along. So that would be the plan. And if you have any other questions, please just email me. But remember that I'm only on Canvas, a couple hours a day, but I'm on Gmail all the time. So if you want a quick response, go ahead and send the mail to my Gmail account, which is joseph.chase1963@gmail.com. Want me to write that down, or do you already have it? Okay, sounds good. All right, anybody have any questions? I have to go back and I'm going to add one more problem about music, but about standing waves and instruments. I'm going to stop sharing now and just take a quick look. How's it going? Do you have any questions for me? Feel free to just unmute yourself.
No questions. I think I just got to finish chapter 11 and then do chapter 12 work.
Okay.
Other than that, that should be done before the weekend. So.
That sounds good. Thank you so much. I know it's a really hard time.
Well, thanks for being willing to do the Zoom meetings. I think that helped a lot in terms of understanding information.
Yeah, no, the Zoom meetings are good. Definitely way more helpful.
Okay. All right. Terrific. Well, it's been very nice having you as part of the class this semester. So maybe we'll see you on the internet. Right?
Are you planning to teach in the fall?
Yeah, that's the plan.
Too? Okay.
We don't know what it looks like.
Yeah.
And CCV wasn't on the chopping block. I don't know if you were following the news through that whole thing. That was a wild ride.
Yeah, that was a little crazy.
Chancellor is, but
yeah, well, I mean, I don't know. I felt like he got set up because the legislature was supposed to have been chipping in 30% of the operational funds and had been chronically underfunding it. He might have been able to do it a little more diplomatically and say, we're going bankrupt here. But, I don't know.
Well, thank you so much for everything. I appreciate it.
yeah,
Yay. Thank you. Best
much.
wishes in all your academic endeavors and life itself. So, and, thank you for taking this class at CCV. I know it's part of, you all have a plan, but I have to tell you, I get feedback from people who go on and do DPTs and get into vet school. And I just found out one of my former students opened up her own vet practice, which is really exciting in Massachusetts. So anyway, it's going to work for you. Keep swinging.
Thank you.
Okay.
Yeah, thanks.
Thank you very much.
Thank
See you
you.
in the fall, possibly.
Okay, great.